Hello, this is Calculus 1, Lecture 15a, Undoing the Chain Rule, u-Substitution. My name is Scott Grizzard from the University of South Florida. So this is really the last major lecture of new material. There's a 15b, which is very important, but it's a reinterpretation of material that we've seen before. It's nice and it's important, but it's not something brand new. So this is the last time we're going to have brand new material. And last time what we did was prove the fundamental theorem of calculus. Next time we're going to look at initial value problems again. Today, what we're going to look at is undoing the chain rule. And this is u-Substitution. And I've actually been prepping you. There's a reason why I've done u-Substitution with limits and then did this u thing when we did the chain rule. I didn't just do the derivative of the outside with respect to the inside times the derivative of the inside. I went ahead and did this u-Substitution thing when we took derivatives. And the reason why I did that, and I wanted to do that, one of the reasons, several, but one of the major reasons is that that's how you undo the chain rule when you take integrals. And undoing the chain rule is a bit more tricky than doing the chain rule. So what we're going to have is like a general method, and then what we're going to have is some tips to try to figure out what we're doing. So let's look at an example. Suppose I want to take the antiderivative of x sine of x squared dx. Now, this had a chain. When I took the derivative, remember, we're going backwards. When I took the derivative of whatever it was, I took a derivative and I had to do a chain rule. So there was some u, and then there was some derivative of u. Correct? So, for example, when I took the derivative of d over dx of sine, when I took this derivative, right, I had the derivative of the outside, so I had a chain. And I took the derivative with respect to u, the derivative of the outside, times the derivative with respect to x of u. And u in this case equaled x squared. So when I did the chain rule, I wound up here with the derivative with respect to u of sine of u times the derivative with respect to x of the inside. So that would be cosine of u, and u was x squared. So I had this u. Now what I want to do is I want to go backwards. So now what we're going to do is we're going to look at this problem in a way of kind of going backwards. Okay? So let's look at this, and it should be emphasized that we're going to play a little bit fast and loose with this idea of this du symbol being an actual thing rather than just a symbol for something. We're going to actually think of it as a piece of a fraction. Let me show you what I mean here. I think here that the original u is x squared. Whatever I did to get this derivative, I think that the u is x squared. So that means the derivative of u with respect to x is 2x. Now, as I said, I'm going to treat this as if this was a fraction. So what I'm going to do is I'm going to solve for dx. So that's going to mean that dx equals, if du over dx equals 2x, that means that dx, I'm going to multiply that side by dx and divide both sides by 2x, is going to be du over 2x. Now, what I'm going to do here is rewrite the problem now with my u. So I think u was x squared. So now what I'm going to do is I'm going to write x sine of u times, now I'm going to sub in my dx, and I'm going to get du over 2x. Okay. Now, something nice happens here. The x here and that x cancel. And now I've rewritten the problem as the integral. Forget the integral sign there. As the antiderivative of 1/2. There's a du over 2, so that becomes a 1/2 sine of u du. And if we recall, I can move this 1/2 across the integral sign. And what I'm going to get is 1/2 times the integral of sine of u du. Now, everything is now in terms of u. Now, I made my chart at the beginning, right? Because I was mindful of what Scott said last week, or, you know, 2 weeks ago when he said, make a chart of your derivatives. It's important. And when I made my chart, I had sine of x plus c. The derivative was cosine. Here's cosine. Here's negative cosine of x plus c, and its derivative is sine. So if I'm looking at sine, if I want to go backwards to the antiderivative, that's going to be negative cosine of x plus c. So I'm going to look at my chart and I'm going to go, okay, that is negative, it's 1/2, because I've still got my 1/2, times negative cosine of u plus c. And whether the c goes on the inside or the outside doesn't matter, because it's just a constant. So c over 2 in this context is the same thing as whatever the c was, right? I got to make a new constant d. They're differing by a constant, so it actually doesn't matter. It looks wrong, but don't let that bother you. That plus c business, it doesn't matter what the constant. If it's c over 2 is as good as plus c. Okay, so now what I'm going to do is I'm going to simplify this a little bit, but I need to sub in my u. So my u, I thought u was x squared. So now I'm going to sub back in my u. I'm going to get negative cosine of x squared over 2 plus my c, my constant for taking the antiderivative. So now what I'm going to do is take the derivative to check. I'm going to take d over dx of negative cosine of x squared over 2. I'm going to get sine of x squared. I've got a chain in here, so I'm going to get a 2x hanging around. And then when I do it, I'm going to wind up with sine of x squared sine of x squared times x, which was the thing I started with. Okay, so I'm going to check myself. And that's basically what we do. Here's the method. I'm going to hunt for the thing that was u. I'm going to make u great again, which is a joke that is probably dated now. I'm going to take the derivative with respect to u. I'm going to take the derivative of u with respect to x, and I'm going to solve for dx. Then I'm going to sub in u and dx, pulling out any constants I don't need. And then what I'm going to do is pray that the things that needed to cancel. If I'm able to do it, I'm going to take the integral and sub back in for u. If I'm not, I'm going to have to go back to the drawing board. And this is something that's very different with the integrals than it is the derivatives. With the integrals, with the derivatives, you have a nice little process. You do this, you do this, there's your answer. Integrals are a little different. You don't have a simple process for taking antiderivatives, right? You have to kind of dig into your bag of tricks. Screwdriver doesn't work. How about this hammer? Bump, 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 bump. No, that didn't work. I've got a wrench. No, I can't get that one in there. So you've got this giant bag of tricks to try, but you don't have any guarantee of success. And there's not just a simple method for doing them. Okay? It's not nice and neat. It's messy. It's more like organic chemistry than it is, like inorganic chemistry or Chem 1. It's like the difference between Chem 1 and Orgo. So you're sitting there trying to find the thing that makes it work. And it's a little annoying, but it's also a little fun, depending on your taste. So that's how you deal with u-substitution. Let's try another example. Let's try some tips. Generally, my first tip is that the inside of the complicated bit is probably u. Okay? let's look at what I mean by this. Okay, so here I've got the cosine of x times e to the sine of x dx. I think u is sine of x. Right? That's kind of the complicated bit. So if I took the derivative of u with respect to x, I would get cosine of x. So if I solve for dx here, I'm going to get dx equals equals du over cosine of x. Now I'm going to rewrite the problem using the u I have before, using this new u. So I'm going to get the integral of cosine of x times e to the u times dx, which equals du over cosine of x. Okay, well that I can do. I've got a chart here. Somewhere along the way I did my chart, right? So I've got sine, I've got cosine, I've got negative cosine. And there's on my chart the thing I want. And now what I'm going to do is sub back in my u. Okay. And then I'm going to take the derivative to check. So I think that the appropriate thing here is e to the sine of x plus c. So I get e to the sine of x times cosine of x right there, and that corresponds with the thing I started with. Okay, let's look at another one of these. This one is a bit more difficult, and the tip here is that if it can be turned into a quotient, turn it into a quotient, and then try to make the thing on the top du. In other words, make the thing on the bottom u, if you can. And then check it. So let me show you what I mean here. I think here that u is going to equal cosine of x. Now, the thing on the top here is sine of x. Okay, so here, if I have that, du over dx equals negative sine of x, which implies that dx equals negative 1 over sine of x. And as you can see, that's, du, okay, I'm going to have to pull out a negative 1, but I can do that. So here we're going to have this is going to be the antiderivative of sine of x times 1 over u times negative 1 over sine of x. I'm sorry, this right here should have been a dx equals negative 1 over sine of x du. I didn't make that mistake everywhere, did I? No. Okay. Times du. All right, now things cancel nicely. I pull out that negative 1, and what I'm left with is 1 over u du. Now, if I look on my chart, 1 over x, the antiderivative is the log of the absolute value of x. And now I'm going to substitute in for the absolute value of u. And I get negative log of the absolute value of cosine of x as such. Now, I want to take the derivative to check. And this derivative is going to have two branches because I'm going to have I'm going to have a what happens if cosine of x is greater than 0, and what happens if cosine of x is less than 0. And I actually need this this cosine. Let me show you what I mean. I actually need this this absolute value of cosine. It's not one that I can get rid of. So if I look at the absolute value of cosine of x, you can see here that that is this function here. And notice it's not defined at a bunch of places. Now, if I only took, let's say I took the negative half of it, I would only get part of this function. And if I did ln of cosine of x, I would only get part of this function. I actually need both of these pieces to get the whole thing, right? It's actually both. So what I'm going to do is when I take the derivative, I'm going to have a place where cosine is negative, and I'm going to have a place where cosine is positive. Okay? So that requires a little bit of being, tricky. So here I've got this. So I take the derivative with respect to x. Right? It's not defined where cosine of x equals 0. So I'm going to have the derivative with respect to x. If cosine of x is greater than 0, this right here is just going to be cosine. Right here, I've got negative cosine of x. I take its derivative, I get regular sine of x. And now I substitute back in my u. I get negative sine of x over negative cosine of x. So both branches work out. The negatives cancel on the negative version, and I wind up with the tangent of x. So this one's a bit tricky, especially in the checking. So, and again, that's the absolute value of u thing coming back in. And I warned you about that, to be careful about that, because you want to make sure you're not taking, when you take this antiderivative, you want to make sure that you're not crossing these, when you do the fundamental theorem of calculus, you want to make sure you're not crossing those singularities where you go off to negative infinity, right? So you want to make sure cosine of x doesn't equal 0. Somewhere in between, you're trying to calculate the area under the curve because that's not defined. Okay. Tip 1 is generally more reliable than tip number 2, right? So the complicated thing is really what you want to start with. So here I'm going to let u equal 1 minus 6t. That's going to give me a dt of du over 6. So when I sub this in, I'm going to get negative, I'm going to get 1 over u to the 4th times negative du over 6. And I'm just going to pull that out. And I wound up with what I started with. Okay, so we checked our antiderivative and we found out it's right. Okay, so that's generally how you do these antiderivatives. There's another kind of problem. Oh, and be ready to break up and combine rules. So let's look at this one. I've got 1 plus x over 1 plus x squared. Now, if let's try some things. So let's say du equals, let's say that u. So what I'm going to try to do here, I'm using my old rules. I'm going to say u is the thing on the bottom. Du over dx is then x. So when I do this, I'm going to wind up with a problem. Let me show you what I mean. I wind up with 1 plus x over u times du over dx. And I can't do anything with that. The things that I want to cancel don't cancel. Right? No! So I need to fiddle with it. Well, this doesn't work. But if this x was there alone, it would work. So let's try to break everything up. So let's get rid of that, and let's instead say that what I'm dealing with is the integral of 1 over 1 plus x squared dx plus the integral of x over 1 plus x squared dx. Now, this one I can do something with, right? This 1 over x squared, that looks familiar. If I had my big table of derivatives here, and I kept going, at some point, somewhere down there on my big chart of derivatives would have been arctan. And I've got that. I know how to deal with that. So this piece right here can become arctan. And this piece, du over x, works. So now I'm going to get this right here. My u now works for this piece alone. And now the pieces I need to cancel. There's an absolute value symbol in there, so be careful. Now, 1 plus x squared is actually always positive, so I can actually simplify that further. I can get rid of the absolute value signs. Okay, so that's an example of one, and that's what I mean by integrals are hard in the sense that you don't have a simple formula that'll work. You have to fiddle with them. And that's annoying. But it is what it is. That's how you do integrals. Okay, or antiderivatives. So again, antiderivatives can be annoying, and sometimes you have to try a couple of tricks. That one is really hard. Okay, well, let's go back to dealing with definite integrals with this. Now, there are two ways to do this. The book has both ways in there. Both ways are perfectly valid. I'm going to show you the simpler of the two methods for dealing with the endpoints, and that is to not mess with them. To do the entire substitution, substitute back in for x, and then treat it like before, okay? So let me give you a little example. When I did the antiderivative of this, it's wrong to do the following. It's wrong to go 0 to pi 1 over 1/2 sine of u du, okay? The key here is that the endpoints refer to x. Okay? So you have to either translate, your book wants you to translate your endpoints into u, okay? And that's a fair way to do it, but there's a much simpler way to deal with the problem. Convert your u back to x. So what I'm suggesting you do is just do your antiderivative on the side. That's what I'm suggesting. So for example, here, I've got the integral from 0. I'm going to do the antiderivative like so. And now, once I've done my antiderivative, oops, don't forget the 2. Now that I've done my antiderivative, I need to convert the u back to x. Right? And the key here, the key piece of info, was that I didn't try to keep it in line with this notation where I did the antiderivative and then I did the bar thing. I didn't try to do that. What I did was I did the antiderivative on the side and then came back and substituted in. And that will save you all of the headache about changing your endpoints, because now I have an antiderivative in terms of x. And now my 0 to pi are still valid. Now, again, you can do it the other way in the book, and I'm sure your Calc 2 instructor, when they do this on the first week of Calc 2, will be like, oh, do it my new way. And that's fine. But here what we're going to do is we're just going to remember to translate back to X and then use my original endpoints. Okay, and that's what I'm going to do in order to solve that problem. So that's how you do it. Just don't deal with don't try to change your endpoints. Just change everything back to X. Do your antiderivative on the side. Put everything back in terms of X, and then apply FTC2, and you will make yourself happy. Your answers will be correct. And you won't try to do this, which is incorrect, because what you're doing is these endpoints are for X, not for you. Okay, so that's what I had for you, a whole bunch of problems. Again, these integrals are tricky. They're not clean and perfect and pristine like derivatives. And Calc 2 is a lot of, well, the first part of Calc 2, because then later you get into series and sequences, and it's really cool stuff. But the first part of Calc 2 is a lot of, try this tool, try this tool, this one. Okay. And so what we're going to do on the last lecture, 15b, again, is we're going to change our way. We're going to do another way of looking at initial value problems using FTC2. It's a beautiful lecture. And that one is the second one for the week. This is the first one for the week. And I will see you for that one. Thank you.